Welcome to Chapter 1 of ICSE Physics, Class 10. Chapter 1 deals with force, and in this video, we're going to finish Part A of the chapter, which is labeled Torque and Equilibria. We're going to be dealing with 5 different subheadings, starting from types of motion to moment of a force, which is also called torque. Then we're going to deal with what's called a couple in physics, equilibrium, and finally, the principle of moments, which is a culmination of what we've learned till then. So let's start off with the first topic that we're going to need to know, which is the type of motions that can be caused by a force. Whenever there's a force, there can be 2 types of motion. The first type is called translational or linear motion, and the second type is called rotational. So let's have a closer look at translational motion. Translational motion occurs when an object moves along a line. So it could be any object, but it has to move in a straight line. But when they mean straight line, it doesn't mean that the entire journey has to be straight. This object could move about any axis. It could be up, it could be vertical, horizontal, or towards the corners. But apart from that, it could even be along an arbitrary path just like this. So over here, although it looks like it's not moving in a straight line, this is still translational motion because there is no rotation. And more importantly, if you were to zoom in close enough, you would realize that every path, including this one, although curvy, is actually made up of very tiny straight paths. This concept of dividing a path into tiny portions that can be approximated to be straight will be very useful in your future classes as you take on physics at higher levels. Apart from that, linear motion can also happen when the center of mass is moving, although there is some rotation. For example, if this ball was to start rolling, the center of mass would still move along a straight line. So that motion would still classify as linear motion. So let's take a closer look at how exactly linear motion occurs when a force is applied. So if we were to actually zoom in to any object which is experiencing a force, we would actually realize that it's made up of many tiny particles, which obviously are molecules, but we're going to approximate them to these boxes for now. When the force is applied at any point, it's applied to one of these particles. This particle then pushes the next particle, which pushes the next particle, and that is how the force propagates through the entire body. Since every particle in a solid is bonded to its neighboring particles, both straight and across, the particles below and above will also feel the pull. So in this way, as the tug goes on by the particles in front pushing the next particles and the particles above pushing the particles below or dragging them along, the entire body is going to feel the effect of this force as you apply the force. The speed at which this force propagates is actually the speed of sound in the material, but we'll deal with that in a future chapter. Essentially, what you should note from this particular example is that irrespective of where you apply the force, as long as the force is applied only in one direction, the entire body is going to feel that force, independent of where you're applying it. If the force is applied here, or here, or here, as long as the force is in the same direction and is the same amount, let's call the force as F, as long as the value is the same, the entire object is going to feel it and move in the exact same way. So that is what is called linear motion. But for that, every single particle has to be free to move. But now let's take a look at rotational motion. Rotational motion occurs when there's a pivot point. In this case, we have the pivot point right here, and the object would rotate like this about the pivot point. Why exactly that happens, we will look in a little bit of time. Now, rotational motion doesn't necessarily have to be about this particular axis. If you were to constrain the movement, instead of this pivot, have maybe a line going through the vertical axis like this, and constrain the object might as well rotate like this, and that would also be called rotational motion. This exact same object could in fact be constrained along this horizontal axis, and in that case it would rotate like this. All of these motions are called rotational motions because the center of mass does not move along a line. The center of mass remains in its own position. But for rotational motion, the center of mass does not necessarily have to stay in the same spot. For example, if we were to have this object, which has a center of mass present right here, this is the center of mass, this little black dot. But we were to then restrain it by pivoting it over here. This is the pivot, and this is the center of mass. What would happen if we then apply a force over here? Every particle tries to push the next particle, and it all works fine until we reach a particle that's nearby the pivot. That particle cannot move forward. And because that particle cannot move forward and every particle is connected, none of the particles can actually move forward easily. Instead, what happens is all of the particles begin to rotate. So then, what happens to the center of mass? In this scenario, our center of mass begins to move as well. But if you actually follow the path of the center of mass, we realize that the center of mass ends up in the exact same place every rotation, which means overall the center of mass is not actually moving. The center of mass temporarily moves, but always comes back to the same position. So that makes this particular motion not translational motion, and instead rotational motion. Another example of rotational motion would be the hinge of a door. Imagine this particular door. If we were to take the door and then move it in 3 dimensions by applying a force on its handle, we would see the door open like this. However, this makes us wonder, why are the handles always placed away from the pivot or the hinge of the door? From personal experience, which you might have had, you'll know that if we were to apply the force closer to the hinge, so let's go closer to the hinge and apply the force here, it would be much harder to open the door. We'd have to apply a lot more force to actually get the door to open. And that's why we always naturally, instinctively try to push the door from as far away as we can from the pivot. So clearly, rotational motion has something fundamentally different from translational motion. In translational motion, no matter where we applied our force, the entire body moved in the exact same way. But in rotational motion, we have to make sure that our force is at strategic locations to get the desired effect or the maximum turning. And that's why we coined the term moment of a force or torque. So what is moment of force or a torque? Moment of a force or torque is basically the turning effect. It is how much of turning is happening when we apply the force. So to understand this, we will take a look at that exact same irregular object. Right here, we have the same object with the center of mass over here and the pivot over here. When we actually apply the force, it's going to turn. But if we apply different amounts of force or apply it at different areas, we're going to get different amounts of turning. So let's figure out what causes the different amounts of turning. To understand that, let's first take a look at how a force is actually moving inside an object that has been pivoted. So if we have a force, you can imagine all of the different particles that are present within the body. Take a look at how these objects are interacting with each other. This particular object, in fact, the right term would have been molecules or atoms. Let's use the term atom. So this atom pushes this atom, which pushes this atom. And when this atom actually moves due to this force that's present over here, this atom gets pulled by this force or this atom to go this way, which pushes this atom, and so on. There's always a pull and a push happening. This particular atom gets a pull from this atom and a push from this atom, causing it to move forward. The same way, this atom gets the push and the push. But essentially, as we go all the way down to the actual pivot, the atom, even though it gets a pull and a push from its neighboring atoms, this atom can no longer move. The moment this atom cannot move, it prevents this atom from moving that much, which then causes a reverse force on this particular atom, which pulls back on this atom, which pulls back on this atom, which pulls back on this atom, and all of the atoms get pulled back as well. So this particular push and pull is what causes the entire body to turn instead of move forward. So clearly, since the turning is happening because of the pulling effect of these atoms, if we were to push further away from the pivot, there would be more atoms that act as buffer between the actual push and the push back or the pulling from the pivot. But if we were to apply the force right here, then the pivot would be very, very strong at counteracting this effect. So the net turning effect, if we were to push it really close to the pivot, would be very, very small. Whereas if we were to push it far, the turning effect would be much larger. Of course, this isn't the exact mechanics of what's happening inside, but we can deal with that a bit later. Essentially, that shows why there's a turning effect. And we also know that if we push harder, we just apply a larger force at the same distance, we would get a greater turn. So let's draw those in two different colors. If we were to have another smaller force over here, we would see that the smaller force produces a smaller turning effect, while the larger force actually produces a very large turning effect. So we could figure out that torque is proportional to the force being applied, and torque is also proportional to the distance between the force and the point or the pivot. But how do we calculate the distance? Remember that this force is not being hindered by the atoms in front of it. It's only being hindered by the atoms below it. The atoms in front of it get pushed normally. And that's why we could apply this force anywhere along this line, and the net outcome, the net torque, would be the same. So how do we calculate the distance? Do we calculate the distance from the point of entry? Do we calculate the point of distance to the point of exit of the force? Do we calculate an arbitrary middle point? To figure that out, we require something that's not going to change and could be calculated for any arbitrary force. So let's take a look at this particular example. If the force acts on this line, the best way to calculate the distance is to find the perpendicular distance from the line of action. This particular force, the line where the force could be acting, is called the line of action. And we would have to find the perpendicular distance between that. This perpendicular distance would always be the shortest distance there is. So we're going to call that as r. And we can actually call that as r for radius, because if we were to have a force continually acting at this point, as this object turns, this particular point that we're calculating as the shortest distance would form a circle. And this distance would be the radius of the circle. And that is why torque is proportional to the perpendicular distance, which is the radius that this particular point would form as it rotates. So since we now know that torque is proportional to F and torque is proportional to R, we can finally find out what torque is equal to. And torque is equal to F into R. This F into R, this is actually the cross product, but that's outside the scope of syllabus for now. However, it's fun to note that torque is a vector because of this cross product. Now, there are two types of multiplications, cross and dot, and we will deal with the dot product in the next chapter. But till then, know that dot products give out a scalar as the output, whereas a cross product gives out a vector. That means torque is a vector quantity. And remember, vector quantities always have a direction. So what is the direction of torque? Because whenever we were looking at the torque is continuously changing directions, or at least it seems like it's always changing direction. If we were to apply the force over here, then we'd notice that the entire object continues to turn. And in order for the force to be applied at the same point, after this object is rotated a bit, the point of application of the force, since it's supposed to be over here, the direction of force would also change. So if the direction of force is continuously changing and the outcome seems like it's continuously changing and rotating, how do we figure out a direction of torque? But we know that it has to be a vector because it matters about the direction of force that's being applied. If we have a force in this direction, but we also have a force in this direction, the net torque would not be just the addition of these two forces. But because this force is in the opposite direction, we'd have to subtract the torque to get the answer, to get what is the final motion of this body. Similarly, if we had the force in the same direction, but the position of the force was down here, even then, it seems like these two forces would be acting against each other and not allowing the turning of this particular object. And that's why the direction of torque is considered to be perpendicular to the direction of motion. That means if we have a torque that's causing an anti-clockwise motion, so that would mean this force, we'll call this force 3, force 2, and force 1. Force 3 and force 2 would be causing torque in an anti-clockwise motion. So in anti-clockwise motion, the torque would be considered positive, and the direction of the torque would be pointing outside the screen. So in fact, the direction of torque would be like this, pointing out of the screen. On the other hand, force F1 was causing rotation in the clockwise direction. So clockwise direction, torque is considered negative. And in that case, it's pointed into the screen. So that is the direction of negative torque, whereas this is the direction of positive torque. In fact, we could do all of it color-coded. So the forces that would contribute towards a positive torque would be forces that are acting over here and over here, whereas forces that are acting here and here would be negative. So essentially, it's divided by the pivot point, and the forces that are above and below make a difference. So torque is always acting along the point of rotation. Always remember, it's always acting along the point of rotation, either in the positive axis or the negative axis. That means going outside the screen or inside the screen. So now we can move on to an example of torque. Imagine we had this screw and we need to tighten it as much as we could. Obviously, we would end up using a wrench. And now, let's say the maximum force that we can actually put out is going to be maybe 5 newtons. All right, so we have 5 newtons of force acting. And this is where we can put it. We're going to have some distance, let's say R1, and the total turning effect or torque is going to be those 5 newtons into R1. Supposedly, we're still not able to tighten the screw anymore. How can we get it to actually turn? We need to increase the torque, but we can't apply more than 5 newtons. So what we could do is we could get what's called a wrench expander. And that would be just like a glove that fits into the wrench. So we could take this wrench expander, move it, and then have it perfectly fit in to the wrench. And now what happens is, instead of applying our force over here and getting that small f into R1, we can apply our force of 5 newtons here and get an R2, which could be more than double R1. And that way, we've actually increased our torque by almost 2 times. And what happens then is that we're actually able to turn the bolt. So that is why it's necessary to know how torques work and how we can actually increase torque. Remember that all of these will have numericals that will be taken care of in the Dayan Academy videos. So after you finish watching and learning all of the concepts over here, you can head on over to practice numericals and get a hang of many more of the derivations off on Dayan Academy. But now let's figure out how we can increase the torque even more by using a perk that we didn't actually notice before. And for that, we have to move on to the concept of a couple. So a couple is generally 2 of anything. So this means that whenever we have a torque, or any turning effect, to be honest, the forces always come in a pair. They always come as a couple. But let's look at why that's the scenario. Let's come back to our trusty irregular shape around which we are rotating, the pivot being right here and the center of mass being here. If we have a force acting over here, remember from Newton's first law that if there's a force, there has to be some acceleration in this direction. But the fact that the center of mass remains within its circle and doesn't actually move, the displacement of the center of mass is 0. That means that there has to be some other force that's preventing it from moving. And we already saw when we looked at each of the different particles getting pushed, we saw that the particles can't move because of the pivot pushing back on this particle. That pushing back from the pivot is actually going to be exactly opposite to force, but of the exact same value as well. So this is just going to be minus F. It's just in the opposite direction. If this minus F was not present, then the object would have to move forward. But since the object doesn't move forward and only rotates, there must be this reaction force coming from the pivot. So in order for any type of rotation to happen, there has to be this reaction force, meaning the minimum number of forces involved is always going to be 2. But when we were calculating the turning effect, we only took into consideration a single force and the perpendicular distance. Why did we do that? That's simply because the perpendicular distance of this reaction force from the point of rotation is 0. And as we know, since torque is equal to the force into the perpendicular distance, since the perpendicular distance is equal to 0, torque is going to be equal to 0, because anything into 0 is 0. And that's why we could completely ignore this torque. But since we know that there has to be a force in the opposite direction, and it's going to be 0 if it's acting across the pivot, why don't we ourselves apply our own negative torque in the opposite direction, or a negative force in the opposite direction, acting below the pivot? This way, our net force would still be 0 and this would not move forward. And the torque, instead of being just force 1 into the distance, it would become force 1 and force 2, which has to be equal to force 1, or the negative of force 1. So it's the negative of force 1 into the perpendicular distance again. So in this way, we'd actually get a lot more torque. And that's what we can call as a couple. The torque due to a couple is always going to be any one of the forces, because both the forces have to be the same, into the distance between the two forces, because it's just R1 plus R2. So it's going to be distance between the two forces. And this is the torque due to a couple. And again, a slightly more detailed derivation will be done on Diane Academy, along with more numericals, so that you can score well in your exams. So a few other examples of couples, or areas where we use it, could be in handles. For example, wherever we have a tap, any type of tap, the handle is always given as an entire round handle instead of just being a single rod, simply because we can then apply one force on this side of the handle and use the other hand to apply the negative force here, and we get twice the torque, and it turns much more easily. And we always end up applying this couple even in areas that we don't necessarily look at all the time. For example, in our keys, whenever we turn, we always use one of our fingers, generally our thumb, to push on one side, and we use the rest of our fingers to push in the other direction below the pivot, which overall allows us to finally turn the key. So that is why we use couples as well. But now that we know what a couple is, let's move on to a culmination of these forces and these torques. And for that, we need to know what happens when they're all equal. And that is equilibrium. So equilibrium is where there's no change of state. So first we have to find out what is change in state. So a change in state is whenever the velocity is constant. All right, this means that if you have an object, right now, this object is in equilibrium because the velocity is 0, which is a constant. Similarly, if this particular object was to start moving, as it starts to move, there's a change in state. But once it starts moving and all forces are removed, it's going to remain moving at the exact same velocity. And that is going to be constant velocity. And that means there's no change in state. Another example of a change in state is when it's rotating. If it's rotating at uniform circular motion, at a constant speed, which we'll deal with in a coming chapter, we can state that it is in uniform motion. So it could be moving or it could be rotating. But as long as it doesn't change the velocity, and the velocity or the speed of rotation, in case of rotation, it's the speed of rotation. And in case of velocity, it's just velocity, remains constant. There is no change in state. But if either of these change, then it's called a change in state. So with that knowledge, we can actually know that there are two types of equilibrium. As you can already see, there's static equilibrium and dynamic equilibrium. So static equilibrium occurs whenever V is equal to 0. That means there is no motion. But for it to be called equilibrium, there has to be forces acting upon the body. The number of forces have to be greater than 1. Because if there's only one force acting, then it's not going to be balanced and it's not going to be an equilibrium. So the number of forces have to be greater than 1 in order for an equilibrium to be achieved. And static equilibrium occurs when velocity is equal to 0. There could be many examples. For example, we could have a block placed on a table. This particular block might seem like there's no forces acting on it, but in reality, there's always the force of gravity that's pulling the entire block down with the mass of the block times the gravitational acceleration. On the other hand, the table is going to be pushing on the block with the exact same force in the opposite direction. And that's because overall there's no motion. So the summation of the forces have to be 0. And it doesn't have to necessarily be just this. Maybe your friend could be pulling on this block because he wants it, but you start pulling back. But both of you are equally strong and pull with the same force. The block isn't going to move, and it's going to be in static equilibrium. Something that's important to note is that in your syllabus for now, you're always going to have forces acting on one single dimension. So it's as easy as subtracting or adding the different forces in opposite direction. But because forces are vectors, you actually have to do vector addition. And you will deal with that in the coming classes, but not in this particular syllabus. That is static equilibrium. But there are other more interesting scenarios of static equilibrium. For example, we could have a beam balance. In this type of a scenario, we have the weight of these 3 balls acting over here, or 4 balls. So this is going to be mass of 4 balls and into the gravitational acceleration. And here we have another force, which is going to be of the block. So the mass of the block into the gravitational acceleration. And overall, if this area was allowed to pivot, there would be 2 torques acting. In order for it to be in static equilibrium, the torques have to be equal and opposite. So as you can see, we have one anti-clockwise torque over here and one clockwise torque over here. And the overall torque is 0 in case of static equilibrium. And we will deal with a lot more examples of this type of a scenario in just a moment as we move on to principle of moments. On the other hand, there's dynamic equilibrium. So we saw that static equilibrium was when V is equal to 0. Dynamic equilibrium is when V is equal to a constant. That means it's continuously moving, but the summation of forces is still 0, or the summation of torques is also 0. An example is a plane. Over here, we can see that this particular plane is always moving forward, but it wants to move down due to the force of gravity. But due to the wings that are present, there's always going to be an upward lift to the plane. So that upward lift is going to push it back up. So overall, it just remains at the exact same height and continues to travel forward. This is called dynamic equilibrium because the velocity is not equal to 0, but the summation of all the forces is equal to 0. This symbol is the summation symbol, which is a capital sigma. Anyway, another example, or a more interesting example of dynamic equilibrium could be the planets. Imagine this particular planet traveling along its orbit around its host star. As long as it's moving at a constant rate, this would be dynamic equilibrium. Because it's moving, but the summation of the gravitational attraction between the planet and its star, along with the centrifugal forces, balance out, causing it to have a net force equal to 0, making it remain on its orbit forever. So with that, we can finally accumulate all of our knowledge to come to the last and final stage, which is the principle of moments. This is where majority of the numericals from this particular chapter is going to come. The principle of moments, in simple terms, is that in equilibrium, it's very important that it is when the entire system is in equilibrium. In that case, the summation of all torques, or we're going to say, or moments, is going to be equal to 0. That is the principle of moments. If you take a look at this example, you can see that this particular balance beam is not moving. If we look at all of the moments that are acting on this particular system, we can see that this ball has a mass. We're going to call that mass of ball 1 times the gravitational acceleration. And this is obviously the pivot point. So it's at a distance of r1 units. Now, something that we shouldn't forget is that this beam itself has a center of mass over here, or center of gravity over here. So its weight is not acting right above the pivot. So its torque is also going to be added. We're going to talk about the mass of the beam into the gravity into this distance we'll call r. And finally, this big, massive ball also has the mass of the ball number 2 into the gravitational acceleration. And of course, it is present at a distance r3. Remember, the distance when calculating has to go up to the center of mass, right here. So that is r3. So overall, from the principle of moments, we know that this is currently in equilibrium. That means the summation of all the torques have to be 0. And from torques, we knew that there's positive anti-clockwise torques and there's negative clockwise torques. So let's look at which torques are anti-clockwise and which torques are clockwise. So here we can see that the torque by this ball is anti-clockwise and hence positive. The torque by the beam is also positive, whereas the torque by this big ball is negative, because this is anti-clockwise, anti-clockwise, and clockwise. You can always see that you can draw it out. This particular point is going to drag it down like this, so it's going to go down and it's going to turn. It's going to go that way. This one is also dragging it down, it's going to turn and go that way. This one's dragging it down, it's going to turn and go that way. It's anti-clockwise, anti-clockwise, and clockwise. So let's actually write the statement. The summation of all the torques is going to be 0 in equilibrium. And all the torques, we'll write down the positive torques first, which is m ball 1 into gravitational force. This is the force into the perpendicular distance, which was r1, plus the mass of the beam into the gravitational acceleration into r. And the last one is negative. So the negative of n of ball 2 into the gravitational acceleration into r2. This is going to be equal to 0. This is the summation of the torques, an addition of all the torques present. So we know many of these and we can figure out the unknown from this particular equation. And that is the principle of moments. And most numericals are going to come from this simple concept. Hopefully nothing was too hard to understand and any example can be deduced by using the concepts that you've learned over here. For example, if somebody was to ask why a droplet of water falling reaches a certain velocity and does not accelerate anymore, you'd have to say that it is in equilibrium. In fact, it's in dynamic equilibrium. The reason for the water droplet to be in dynamic equilibrium is because there's a force due to gravity pulling it downwards, but there's also air resistance and friction pushing it upwards. thereby making the total force equal 0. So different scenarios could be given, and all you have to do is apply what you've learned over here and answer those questions. They might ask why different scenarios is easier than others. For example, why is it easier to open a bolt with a double-sided wrench than using a single-sided wrench? That's simply because we are forming a couple when we use a double-sided wrench and doubling the amount of torque that we're getting, allowing the rotation to happen. If any question comes as to torques, I'm sure you'd be able to do it just by knowing that torque is the force into the perpendicular distance between the line of action and the pivot or the axis of rotation of the torque. There could be various questions like the pedal of a cycle is always present much larger than the actual gear that it's connected to. Why is that the situation? It's simply so that the radius where you apply the force can increase, and hence you get a greater torque while turning your cycle. So you have to apply what you've learned in these types of ways to give the answers. Finally, you have to know the translational and rotational motion, and given in a scenario, you have to be able to deduce whether the motion is actually translational or rotational. Easiest method is by following the center of mass and seeing if the center of mass is moving away in a line or if the center of mass is constrained to a point or to a circle. And with that, we can conclude section A of the chapter force, which was torque in equilibria. Any doubts, leave them in the comments. If we've missed out anything or you want anything to be added, please let us know, and we will make other videos that cover up all of the missed concepts as well, so that once you take this particular course, you shouldn't have to ever struggle in your exams. Hopefully, you will be able to answer any question paper from any school or the board with ease and solve every numerical once you've completed the numerical side or the more practical approach that's over on the An Academy. Stay tuned for the next chapters and the next portions of the chapters coming up very soon. Stay safe, take care, and goodbye.